Tonight's Thursday evening, and it's been a very exhausting 2 days. It's hard to believe that we're only half done, and yet we've all had a lot of opportunities to see a lot of amazing presentations. And it's just too bad we can't see it all. I mean, it's really a shame. And on the other hand, it's been great to have so many talented people come here and share all their knowledge. Tonight is kind of, I guess, one of the highlights of the week. I don't know, has it been 6 years now? The NPA has chosen, since the death of founder John Chappell, to honor his memory and the founding of the NPA by having a special lecture named in his honor. And in that tradition, I guess we want to set apart one paper, one lecture as kind of being the special one, the one that we all want to pay attention to. And so this is it. And before, as just a little preamble to that, I've asked Rick Jesh to come in up and say for a few minutes a little bit about John Chappell and something about the founding of the NPA. For those of you that are kind of new to it, this will be a chance to learn a little bit of our heritage as the NPA. So Rick Jesh, come up for a few minutes.
Thank you, Greg. Hi, my name is Rick Jesh, and I've been asked to talk a little bit about the early days of NPA, what I remember of the times when it was formed under John Chappell's leadership in the early 90s. As I look around, I see some of you here today who were there in those early days. And it's wonderful to see you guys here, but it's even more exciting to see all the new people, all the new ideas that are coming. In 1992, my good friend Lee Coe asked me to go with him to Santa Barbara to the 78th annual convention of AAAS. I wasn't a member, and so I thought, gee, I haven't never been to one of those and it costs money. But he said, that's all right, I'm a member. Just stick with me. And that has taken me a long way. He also requested that I videotape his presentation, and I videotaped some of the other ones, and I'm so glad I did because I still have it. And David actually put one of those early tapes on, and we have remembrance of John Chappell through a great presentation he did. Francisco was probably there, I think Ron was there. At that time, my friend Lee Coe had arranged under the AAAS auspicious to have a debate with a man named Lewis Carroll Epstein about the validity of Einstein's special relativity. And that's where I met John Chappell. John clearly pointed out the parts of special relativity that didn't make any sense. He went on to reveal that many, himself included, had been, shall we say, pushed back because of establishment practices that didn't accept those kinds of offbeat ideas. I think those days are behind us. I don't consider my friend a scientist, but my friend Lee pointed out something that I had not allowed myself to think. I said to him, I don't really understand all that relativity stuff. You know, like how twins would be a different age if one went on a trip and came back. And he said something to me like, that's good. It means you haven't accepted all the rubbish that might pass as logic. Those weren't his exact words. I couldn't think of those.
Yeah, paraphrase.
I felt like a huge weight had been lifted from my shoulders, and I was allowed to think the thoughts that you should think. He changed my way of thinking about natural philosophy. I can't remember when I had heard this quote before, but you probably have too. If quantum mechanics makes sense, then you don't really understand it. Maybe it's fine, I'm not sure. In 1994, I went to another conference in San Francisco, and that is the conference where I say the Natural Philosophy Alliance emerged as an organization. People were walking out from the presentations just like we did this afternoon, and we thought, wow, that was a great We brought out a lot of great topics. People were excited. It was magical. And someone, I think it was George Curie, said, you know, we're good enough. We should have an organization of our own. And then the next thing was, well, sure, what shall we call it? And one of the few people there came up with Natural Philosophy Alliance, or it came up within a couple of months. And that was what I call the first conference. And John Chappell admitted that it was a good time to do that, and the NPA was born. He did most of the organizing and coordinating, but was soon helped by a lot of good people. But I cannot stress the amount of work and determination that John put into those early days. And it was a lot of work, and he was very dedicated to it. He had a regular job, like most of us do. And thanks to all those people who did all that work in the early days, we are blessed with the organization we have now. And I cannot stress too much the work that David is doing and Greg is doing, because this whole organization, I saw it spring to life a few years ago, and I'm quite amazed, and I'm so honored to be here. I'm not fit to untie the sandals like most of you guys. John had a few principles that he went by, and they're just a few, but they're very important. And if you knew him, you knew that he lived by these principles. First was tolerance. Listen to others. Don't let your preconceptions get in the way of understanding. And another main one, logic. Try to avoid contradictions. So in conclusion, I would just like to say thank you, all of you, for listening, being tolerant, and helping each other.
Thank you, Rick. I hope you enjoyed a little tour down memory lane. And I would like now to introduce someone I just met a year ago at a conference for the first time, and I've been delighted to get to know him. I told him the first time I saw him that you sound exactly like Desi Arnaz. And he said, "Who's Desi Arnaz?" But anyway, I'm so appreciative of the experimental work that he's done, and a lot of these things that he's been working on were long before the MPA even started, and that he has continued to do and improve on some of these ideas, and I just am challenged and pleased by that, and hope that he'll continue to do that excellent type of experimental work that he's done. So I'd like to just bring up my friend, and I hope that you'll enjoy listening to the John Chappell lecture this year, Francisco Goode.
Thank you, Greg. Just a little word about that first meeting. I remember at the end of the conference we met in a little room to discuss some discrepancies about ether. Do you believe in the ether or not? I mean, everybody said something, but when it came the turn of Domina, she said, "I don't use that word." So I understand something here, which is a very isolated problem. Actually, what I've been working for years, almost 30 years, is my experiment to be shown on the side. So that's really a continuous life enterprise. This is just something that occurred to me teaching astronomy, which I'm not an astronomer. I just read one chapter ahead of my students. My students are non-science majors, so no matter how ignorant I am, they're more ignorant. So if I write an equation on the board, they get horrified. And teaching, for 4 or 5 years now, it came to my mind, because I am a physicist, so I teach astronomy with a physicist's mind. How can we have a Doppler-shift of an absorption line? An absorption line is a dark line, it's no light. How can it shift in any way? And they were very much used. So this was the seed of this isolated problem. I took this from the astronomy book. It's the same title again. And we're going to see some situations to understand this problem, which I hope you understand that it is a problem. And maybe my solution, you like it or not. Okay? So let's keep going one by one, background, broader, elementary solution. This one is one I found in the internet, one student asking about this. How can absorption have Doppler. So at least one person thought it was a problem. And it was given an answer in this web page. I didn't put it. It's from NASA. Okay, so then two more solutions. I'm gonna have two scenarios: a single moving nebula or a moving star is a moving atmosphere. I'm gonna use this as the type of proof that I can use. It's simple problem, so okay, then to analyze classical, we're going to summarize the problem with relativity and this web one solution. And the consequences, this is the only positive part. Okay, I'm going to discuss some little problem of classical, relativity and quantum mechanics. And the conclusion is that the classical theory wins. Okay? So this is one more black spot for relativity theory. So that's the negative side. The positive side is this diffraction experiment, because I was doing this last year, remember? This Brazilian experiment, they tried to prove the motion of the Earth by diffraction experiment. And they didn't give no theory. So I think I have the theory, but I couldn't replicate the experiment. They have the experiment, they do not have the theory. So, okay, so I'm gonna treat you like my students. I'm gonna suppose that you don't know. So don't be insulted, because you know what an absorption line is. But anyway, in astronomy, you have three kinds of spectra. When you have a very dense body and you pass through a prism, you get a continuous spectrum, a rainbow. If you have just a cloud of gas emitting enough energy, you're going to have discrete emission lines. But if you have a dense object passing through a colder cloud of gas, this is going to act like an absorption filter. So then you get the rainbow and the absorption lines.
Both.
This is the absorption spectrum. Okay? And this was discovered, keep going, by Fraunhofer in 1814. Here's Newton, his famous experiment with prism. He projected on a screen. But Fraunhofer, he was a gifted young fellow. He had a terrible accident, almost died. But the Maximilian, the emperor of Austria, gave him money. And he used money for more experiments. So voila, he discovered this in 1814. Because instead of projecting the rainbow to the screen, he looked directly to this rainbow. That's dangerous to do. So he saw a rainbow and these superposed absorption lines. So these are all Fraunhofer lines for obvious reasons. Okay, that's what historical model. Let's keep going. So what is going on here? Here's the sun, here's the atmosphere. Sorry, but it looks like a fried egg. That's not my intention. The sun, for example, emits 656. I'm going to use a specific case because this is very well known in astronomy. This is the signature of hydrogen. When electron jump from the third to the second level, it emits 656 nanometers, a red line. Okay, suppose that the atmosphere has hydrogen. So this colder hydrogen can absorb the 656. So this is absorbed. So it produces a dark line at that precise wavelength. And it has more lines, but this is going to be my example. So this is what Fraunhofer found, and there's no explanation. By the way, this line is not totally absent of light. What happens is that the atom absorbs and then immediately remits in all directions. So the light that goes through is minimal, but some goes through, but most of it is scattered. Okay? So that's why it appears dark. Let me read it. The sun emits a rainbow spectrum, then hydrogen atoms in the solar atmosphere, which are the red dots here, absorb the hydrogen alpha line, that's the name, 656 nanometers, which appears as a Fraunhofer dark line in the observed spectrum of Earth, exactly at that wavelength. In reality, the H atoms emit the 656 radiation in all directions, thus weakening the intensity that reaches Earth. So we call it an absorption line. A little bit of the background of the Doppler effect, which is not related to this, but it's going to happen. This is the classical equation that refers to the emission velocity and the detector velocity. And the plus minus signs, depending if they come together or they separate. If you have, if this is for line of sight coinciding with the motion. If there is an inclination, they have to introduce the cosine of the line. Okay? But you see, I didn't include the plus minus sign here because with this convention, when you are moving away from the light, you're going to increase the wavelength without need to refer to any detector. And this is very important. Doppler effect doesn't need emitter and detector. You can have a Doppler effect just with an emitter. If the emitter goes in opposite direction to the light, then the angle is 180. You put 180, you get minus minus, so it's plus. So you increase the wavelength when you're going away. Okay? And the same thing happens with the emitter, with the detector equation. So this summarizes everything better than this. Now, I want to split this equation into 2 steps, because when you demonstrate the Doppler equation, you have to go in 2 steps in the classical theory. So this is the emitter equation, and this is the detector. And it appears on the top and on the bottom. Of course, when you combine them, this cancels, and then you end up with this single equation in terms of the velocity of the emitter and the detector. Of course, I put here this case, so minus minus is plus here, minus minus is plus. So if the emitter velocity and the detector velocity are different, you're going to get a lambda prime different from lambda 0. But if these 2 velocities are equal, which is the case of moving together, then you don't get any change of wavelength. You go back to the original natural wavelength, the emitted wavelength, lambda 0. Is that clear? I put it in this. It's very important that we understand that the Doppler effect has 2 independent moments, the emission and the detection. When you prove it, you have to proceed that way. Okay. In the next one, I did the same thing for the relativity formula. It looks very much the same, but it's only relative velocity between emitter and detector. It's a single entity that appears here and here with the signs interchanged. Okay? So that's what it is. Or you can just take out the speed of light and it becomes like that. You can also put the directional sign in case there's no alignment. It's the same as the classical theory, it's the same meaning. And this can be rewritten with the gamma factor in front. It's exactly the same equation. Okay? You can do the algebra, it's the same. With the cosine direction angle here. Okay? You see there are different signs, so it's not unity. Even if there's only one relative velocity, it will have some value. The only way that relativity gives you a 0 value if this relative velocity is 0, because then you get 0 is unity. Okay? And that's what relativity says. If one thing is moving together with another one, there's no Doppler effect. Whereas the classical theory says, oh, there's a Doppler from the source and a Doppler with the detector that cancel each other. It's a very different thing to say that the 2 Dopplers cancel than to say that there's no Doppler. This is the 2 theories that Ericsson was mentioning. Okay. Anyway, keep going on. This is just the theory. This is how they detect something moving away from us. I'm going to concentrate exactly on this problem. The 656 line is going to go to 670 if the source is moving away from us at 6403. Okay? This is a cluster of distant galaxies. And of course, all the other lines are going to shift also. But I'm going to concentrate on the 670, so please keep these lines in mind. Okay? So what is the problem? Okay, I'm going to summarize again the whole thing. Astronomers use the Doppler effect to tell the velocity of stars in nebula, etc. They do so by usually considering absorption from alpha spectral lines, which appear as dark lines against a continuous line. In other words, all these spectral from moving stars are absorption lines. I have never seen an emission spectrum. Okay, which is very interesting. Then this happens when the light from a star is absorbed by its own atmosphere. So we have the emitter is the star, the detector is the atmosphere, and they're moving together to us or away from us. So there's no relative motion between the emitter and the detector. Okay? Can you see the problem there? Keep on. So the problem is, how can a dark line absence of light energy be shifted in any way, either to the red or to the blue? An emission line can be Doppler-shifted, but an absorbed line is the absence of light. How can it be Doppler-shifted? Okay. Now, at this point, there's one more, I think. Okay, stop it there. Because I was presenting this to my brother, and he immediately gave me a solution. So I'm going to give you 1 second or 2. First, do you see a problem or not? If you don't see it, no solution. But is there any solution that appears to you? How can you have an absorption line moving? Say to the right. Yes.
Everything moves. Everything scales. The frequency scales. The wavelength scales. So it's the whole spectrum scales. all the emitted light goes up, and the whole goes up also.
That's the standard answer. In fact, that's what I found in the web. Okay, I call it web 1, 2. Any other idea?
I would say if emission absorption is a two-step process, then this is really a four-step process. In other words, you have the emission absorption by the interfering medium, and then you have the emission by the interfering medium, and then absorption by the receiver.
Wait a moment. That's a very important thing. And there's no emission by the interfering medium. The cloud of the star is a passive. Either you absorb one line and the other ones just keep going. That's very important. In other words, the cloud is not an emitter, it's only an absorber. This is physics. Okay? It's very important, because otherwise there's no problem. The problem is precisely the only emitter is the star. The cloud is a passive filter. Okay? Now the solution that you advance is exactly what Web 1, this is a Paul Stein person from NASA, answering to this kid. So let's read the solution as he says, imagine an absorption line in the spectrum of a star. To its right and left in the spectrum are bright emissions, which get shifted by the Doppler effect due to the relative motion between the star and us. Both lines in the same direction, the red and the blue. Would the dark gap between them shift the same way? It would, if the dark absorption feature is caused by the gas at the star. So that's exactly what you said. You agree that that's what you have in mind? Everything shifts. It's like a window. You cannot move the hole, but you move the frame. Right? Okay. This is a summary of what is being said. I'm going to be very specific. With a star receding at this velocity, the wavelength 656 is going to go to 670, but it's going to be absorbed. 655 goes to 669, and 657 to 771. Plus minus some decimal, but this is what you're thinking. The neighbors shift, so the hole that is absorbed is going to appear like a shifted hole. Good. Now, what is the problem with this solution? Here's my criticism. I don't pretend that you understand it first sight, okay? I'm going to read it, but the whole talk is to see why this is a problem. The problem with this answer is that it assumes that the absorbed dark line is already produced without explaining. And then they speak of a Doppler-shifted as happening afterwards. In reality, the Doppler stretching occurs before absorption at the atmosphere. Light emitted by the star is redshifted and then it hits the atmosphere. So a 656 photon stretched to 670 cannot be absorbed at the atmosphere, otherwise quantum mechanics is violated. Now, that's the way I explained it. If you don't understand it, it's okay because it's a little bit complicated. Emission occurs at the star, and the Doppler shift, the star is going away. All the wavelengths are going to be Doppler shifted, all of them, including the 656. So 656 goes to 670 before being absorbed by the atmosphere, and it cannot be absorbed because an atom of hydrogen has to absorb 656. It cannot absorb 670, or you violate quantum mechanics. Is that right or wrong? Are you?
I want to say off the top, it's a function of whether the velocity is moving of the star is causing it, or your recession velocity is causing it. Is that right? In your model?
It could be an alternative, but when you see this redshifted whatever lines, we say the star is going away from us. Amazing. We could say that we are going away from the star, but the interpretation is that the star is going away from us.
Francis,
yes.
Is this atmosphere not traveling with the star?
Yes, they're going together, and that's the problem.
Together. Well, I think that solves the problem.
That is what? You don't think there's a problem there? No.
She said it solves the problem.
Oh, good. Maybe you're my brother. How it solves the problem?
Because this whole absorption transpires, or can be viewed as transpiring in a coordinate frame with the star, and there's nothing strange about the absorption at the correct frequency.
Sorry, because you're talking like a relativist. No. This is the other alternative. Relativist said, from the point of view of the atmosphere, there's no Doppler, because there's no relative motion. Therefore, 656 is emitted, therefore we swallow 656, no problem.
Well,
right? They don't recognize that there's an in-between stretching of the wave. Now, is there an in-between or not? That's the problem. You're not discovered. Yes.
I was just going to say that the photons emitting from the sun don't know what their speed is relative to Earth.
Okay.
So therefore, they can't do this shifting. We observe the shifting at Earth because we know what our speed is relative to that star.
No.
The star doesn't know.
We don't need to know our speed. We see a shift and we say that star is going away with this velocity. By the way, the sun is not going away from us. It's at the same distance, okay? So thanks God Fraunhofer discovered it with a no moving case. But I'm glad that you pointed to this other idea that there's no Doppler between the star and the atmosphere. That's exactly what relativity is going to say, but not classical theory. Yes?
The way I reconcile it is that the Doppler between the source and receiver, whatever goes in between, is expressible not only in frequency domain, but in time domain. It's the time delay, time derivative.
Yeah.
At that point, it doesn't matter where that cloud is.
That's right.
It's going to do the right thing because
That's right.
with the star, it's going to produce the right pull and in frequency, and it's going to produce also the right time delay, time derivative.
No problem. The time is there's a time interval, but it doesn't matter how much time. It could be a big star or a small time, doesn't matter. And with that, the time is very important for me. It's two physical processes, okay? Let's keep going and we'll see the whole package. So, as a first scenario, let's do something much easier. A single cloud of hydrogen nebula, and there's a very dense quasar really billions of years away. Now here we are. This is in the astronomy book. This is the other case. They can tell the motion of the cloud because again, the absorption lines are shifted. Okay? So if there's no motion, oh, no problem. Keep going. If there's no motion, okay, no problem. You have the quasar emits all kinds of radiation, a rainbow. Then this is hydrogen. It absorbs the 656. Therefore, we get a dark band at 656. Okay? So no motion, no problem. It's like the sun. Okay, I put here the white line. In the next one, now we have motion of the nebula away from us. Okay, here's where I want to create my solution. So let's see if you agree with this. The nebula goes at the same velocity from before. So here's the quasar emits all kinds of things. It emits the red 656. It emits another one. Now, how is the nebula going to absorb 656? Because when that nebula moves, the 656 appears as less than 656. It's being shrunk. If there's a Doppler effect, because this is going against the light, in fact, 656 is not going to go to 642, I calculated. And it cannot be swallowed. So the nebula cannot swallow 656 because it looks like 642. It has to swallow 670, that by the Doppler shrinking effect is going to appear like 656. And then, of course, the light that keeps going misses the 670, even though the nebula eats it as 656. Does that make any sense?
Yes, it does.
Now, you agree with this? My battle is won. However, there's a little reservation here. And I'm going to talk about the end about the quantum mechanical aspect. Because this means that this hydrogen atom that is ready to absorb 656 can process 670 by the mere fact that it's moving against the light and is seeing it as a 656. Now, have you ever seen that a photon is what it appears by Doppler effect? I have never heard any quantum mechanical theory of the Doppler effect. So you have a chicken that is too long. You are moving, it becomes shorter, now you can eat it. Okay? But I did find a little interaction between Bohr and Schroedinger and Dirac in the 1918s, where Bohr, in fact, pointed to a problem when an atom emits a photon, it recoils by momentum conservation. And then he said there are two frames of reference, one before and one after. So there's a problem here, he said. So he's tackling the problem of quantum mechanics, emission or absorption, and Doppler. It's the only paper that I found. This is 1918. Immediately, Schroedinger in 1922 said we have to modify the relativistic Doppler equation. And he introduced the two velocities, V1 and V2, before and after the process. And he gave very complicated, I didn't make the question. But then Dirac in 1924 said, no, you don't need to do nothing. The formalism in 4 dimension takes care of it. And I don't understand what Dirac said, I respect. But this little interaction between them is very instructive, because then finally in 1932, Fermi produced a real theory of the Doppler effect from the quantum mechanical point of view. And he wrote 6 Hamiltonians, and he quantified motion from the point of view of quantum mechanics. I have never heard anything like that before, but it was 1932. I'm going to talk again about this. So, with the provision of the quantum mechanicians, we can say that the atom can process by Doppler effect the photon to the proper dimensions and then absorb it. Okay, so that takes us a working hypothesis. That being the case, what I need the recession. The cloud is now moving away. So I already said it, right? Yes. The 670 becomes shrunk to 656. It's absorbed at 656, and then the 670 cannot go to Earth. So we see the line at 670. So we say, oh, the cloud is going away with this velocity. And that is standard interpretation, except that nobody worries how can you absorb 670. That's it. And I did worry as a humble astronomy teacher, but with some knowledge of physics. They don't care about it. Just 660, the cloud is going away. Okay. So that being my solution, you see, the cloud absorbs the emitted 670 nanometer radiation in the form of 656 radiation as shown by the Doppler effect. That's my conclusion. Now we keep going. Okay. That was the nebula alone, moving with respect to Earth. Now this is the problem. The emitter is not a quasar far away, it's the star itself. And the filter or the absorber is the atmosphere. And they're gonna go away from us at the same velocity. So now there's no relative motion. This is the problem. Okay, so I'm gonna apply the same solution as before in this situation. If there's no motion, again, no problem. You absorb 656 emitted by the star, the atmosphere swallows it, and then there's a dark line. Okay? Now, when we put motion into the story, the same thing happens. The star emits 656 stretched to 670. Now, the atmosphere cannot swallow 670, but the atmosphere perceives 670 as 656, and then it can swallow it. Again, you see, the atmosphere is shrinking while the star stretches. So there's a double Doppler effect. So the atmosphere believes that the photons are 656. This is a fictitious wave. But in effect, by the Doppler at the cloud, the 670 are shrunk back to 656. And then it's absorbed. But the light that keeps going to Earth is a dark spot at 670, because this is the one that has been eaten by the atmosphere. Okay? So here's our 670, everybody's happy, oh, that star is going away at this velocity, and they don't realize that the detector, the atmosphere, and the emitter are moving together. And there's a Doppler effect without relative motion. That's what connected me with the Brazilian experiment. But let's process this a little bit more. So the 656 nanometer waves are redshifted and enlarged to 670, like I draw here. In the space between the star and the atmosphere. This is crucial. This is happening between the star and the atmosphere. And also all the way to Earth. There's a stretching of all the other wavelengths, including the 670. Does the atmosphere absorb 670? The atmosphere? It cannot, according to quantum mechanics. So what happens is, as the atmosphere moves with the star, is that the 670 waves are perceived by the atoms as 656 shortened due to Doppler shrinking, since they travel against the light. You see? You travel against light, you're going to shorten it. That's the key thing. Due to Doppler against the light. And at 656 photons, the hydrogen atmosphere can absorb them, although for Earth they disappear, leaving a hole at the 670 line. Okay? So there's a double Doppler effect. The star emits 656 is stretched because it starts going out and the light is going in the opposite direction, 180 degrees. So they're stretched away from it. Now the atmosphere is the opposite. It's going against the light, so it shrinks 670 back to 656. Happy, hydrogen atoms are happy. They eat the 656, but the light really that goes to Earth is 670. So the whole is at 670. Okay. Okay. So keep going on. Now it's easy. You start moving on. This is a repetition of what I said. The interpretation by classical is that there are two steps for the classical Doppler. So even though the emitter and the detector velocity are equal, yes, a detector in the atmosphere will perceive no change. That's what you were saying, Cynthia. She was saying this from the point of view, well, I don't know what your theory is. A classical theory will say, no, if you're traveling with this star in the atmosphere, you perceive no Doppler. Right. You don't perceive it, but it exists in between. That's the difference between detecting and existence, between numbers and physical explanation. Okay? So this is the two steps. Let me see. This is again a repetition of what I said. The simplicity waves are perceived. Oh no, okay, keep going because this is just an equation. Now, relativity. So far I see that classical theory that this double Doppler effect can solve from. How about relativity? Okay. Relativity says there's no Doppler. This is moving with this, the equations, no relative velocity. So 656 is perceived by the hydrogen atom like 656. No problem. Like classical theory. But they don't accept that there's a Doppler here. Okay? Whereas there's a Doppler. From the point of view of Earth, distortion happens from the very beginning. So it's like a double answer. From the point of view of the star's atmosphere, there's no Doppler. From the point of view of the observer at the Earth, there's Doppler. Again, the typical duality of relativity theory. And we never know, but is there any Doppler here in this space? Physical space separated by two instances of time. So, for relativity, there's absolutely no Doppler effect between the star and the atmosphere. 656. The atmosphere could absorb 656, so there's no problem, as you said, Cynthia. But that would produce a dark line at 656, not at 670. If you absorb 656, how come the dark line appears at 670? There's no further Doppler shift, there's no emission. This is a, okay? Even if you, okay, but you might shift the other ones. Let's keep going. Doppler exists only between the star atmosphere and Earth, producing 670 and larger than. So the question is made, how and where those 670 nanometer photons are absorbed? The redshifted 670 waves as seen from Earth cannot be absorbed by the hydrogen atmosphere. Again, quantum mechanics violation. So somebody in the Earth says, oh, 670 is here. So that cannot be absorbed by the star. Okay. Relativity said, oh no, there's no shift. I absorb 656. But then the dark line should be 656. Because the rest of the process doesn't shift that line. Or maybe it shifts, it appears shifted. Because of the background. So let's keep, that's the web one solution. Let's keep going. This is the equation of relativity I already mentioned. Keep going. Because you can use it between emitter and detector of the star or between the star and Earth. Okay, there's a double viewpoint. Let's keep going. Okay, this is the hybrid answer. I call it hybrid because this man from NASA, even though he's not invoking relativity theory, he is actually using it. Okay, so this is the idea that the neighboring wavelength shifts. Okay, so let's replay this answer. The answer given by web 1 to the student is that the 656 photons are absorbed as the star's atmosphere as it should be. Okay, no problem. But then the whole white light rainbow is shifted to the red. This is the gray. This is the white or gray light. All of them are shifted. So this background spectrum shifts everything. Everything from 400 to 700. For example, it goes to 409 and 700 to I calculated 715. Giving the impression that the absorbed 659 is located at 670. You see? It's really absorbed here, but it looks like since the rest shifted, it appears 670. That's exactly what you said, right? And what one said. Okay. If that is the case, however, look at the region between the star and the atmosphere here. Crucial area. There is a Doppler shift for all radiation, white line, except for 656. How can that be?
How convenient.
You say that everything is shifted. Okay, so everything includes 656 before absorption. Is 656 not shifted here?
Yeah.
Is it shifted or not? If you say that all of them are shifted, why 656 is not shifted?
Everything is shifted, nothing is shifted until you get to the atmosphere, and then shifted up.
No, the shift occurs at the emission. Of the star. There's no shift. The atmosphere is passive. There's no emission of the atmosphere. It's just pure filter.
Shift is I don't get it.
It-
I don't want to.
Okay. No, the problem is that there's a contradiction. You tell me, you absorb a 656, but everybody else is shifting. What a moment. Why 656 is not going to be shifted to 670 and then you can absorb it? Yes.
I like your solution, but if I take your classical equation, then the shift is either from the source or the receiver. If I have an absolute space, and then if I blame my motion all on my receiver, I think then that picture would work, but only under that condition. Is that,
The word,
you know what I'm saying?
you attribute
In your
the...
classical equation,
Yes.
let's assume that in absolute space that star is fixed, but that I am moving on the Earth at some high rate.
Yeah.
Then I think that the Webb solution would apply, but only if
That's
there's-
right, because then everything is shifted, including...
Yeah, right.
But the interpretation is that they started moving away from us.
Yeah, the special relativity won't work both ways.
Okay, let's keep going. It seems that relativity cannot explain the existence because he has to make an exception for 66. Everything shifts, but not 66, so they can solve it. Okay. There's another. Okay, so there's no Doppler-shift for this guy, but there's Doppler-shift for everybody else. Before you hit the atmosphere, that's the problem. Okay. Okay, keep going. So summarizing the difficulties. What happens with relativity and Webb 1 is that they shift from one frame to the other at their own convenience. Thus, using the atmospheric frame of the star, they say there's no Doppler. So the H atoms there can absorb 66 photons in agreement with quantum mechanics. Then switching to the Earth frame, they say there is a positive Doppler effect. So all wavelengths shift to the red, making the 656 hole appear at 670 because 655 and 657 go to 669 and 671. Keep going. But this duality contradicts the fact that the 656 photons are also Doppler shifted immediately between the star and the atmosphere, just before absorption occurs. Okay? Now, there's another possibility. How about some 643 photons emitted by the star which are shifted to 656, and then they could be absorbed by the H atoms by the same reasoning? But that would produce a dark line at 656, not at 670, which is what is observed. Okay. And in fact, the 642 will be again emitted. No, it could be absorbed. I said 653 would appear. Oh, yeah. The 653 can be stretched to 656, okay, and absorbed. But actually, the star shrinks them back to 643, so it cannot be absorbed here. Anyway, it's another solution. Keep going. You see how is time going? Yeah. Okay, this is a summary. This is now in a table form all the wavelengths that are pertinent, including 400 to 700, the limits of the visible range. I put that 642 being stretched to 656, and I put the three neighbors, the 656 and the two neighbors, shifted to the corresponding wavelengths here. And this is a blue shift because this is 670 when the nebula was moving away from us, it shrunk it back to 656. Okay, so this is the only blue shift. Okay, I want to explain, I put here all the shift calculated with three significant figures. Here's the classical formula, and here's the relativistic. This is slightly different in this fourth place, fourth significant. But I rounded up for discussion, so they're both the same set of lines. Okay, according to that, then what happens, the classical interpretation is this. 656 is stretched to 670, but it cannot be absorbed by the photons. But the photons perceive them as 656, but that's a blue shift. So then it can be absorbed. So it absorbs it, but the hole appears at 670. Okay? That's the classical explanation. The shrinking, the stretching and shrinking. It eats the chicken in the proper size, but then the light itself that goes to Earth is missing, remember, missing 670. Okay. The relativistic diagram, keep going, is this one. It says, okay, this can be shifted from here by stretching. If you absorb it, then you produce a hole at 656.2, which is not observed. How about 656 being stretched? It cannot be absorbed here. This other process where you shrink 670 to 656 and eat it, the relativity theory doesn't accept because there's no Doppler. Relativity, there's no Doppler. Okay? So this is the only thing that can happen. If there's an absorption, it's absorption from this lower guy stretched to 656, and you should have, but this doesn't happen. We don't see this 656, we see 670. Okay. Finally, okay. This is a little animation, but of course in 2 steps of the whole thing. I just put half of the atmosphere, and this is the normal case of 656 absorbed. We have a dark line here. Okay, that's the theory. Now you play the next one. It's moving, and there it is. You stretch here, and this atmosphere believes it is 656. But the missing light is 670, and this is the classical theory. I'm just reiterating it in 2 steps. Let's keep going. David? Hello? Okay. So this is the negative part of the paper. I'm blaming relativity theory that cannot solve. I'm blessing classical theory. Now, a positive consequence, because remember I tried to do this experiment, and I couldn't. But I know that the theory is fabulous. So what is this experiment? People who didn't hear me last year, look at the experiment. It's very nice. According to the explanation given, we see that the classical Doppler effect really exists between an emitter and a Doppler, even if there is no relative motion. Okay? So even if the formula tells if this is equal to this, there can be no Doppler, we know that there's an effective Doppler in between. The habit of referring to the formula like this, as if emission and reception were simultaneous events, hides the time interval that separates them. These time intervals show that both events are independent of each other. They occur unilaterally. You don't have to have a detector to have an objective Doppler effect. That's my point. You need 2 things. One thing will produce a Doppler. Of course, that's absolute thinking. It is often referred to search for an experiment affected by only one of the 2 guys, the emitter of an isolated Doppler effect, and through the change of wavelength or frequency, detect the motion of the emitter from within the frame of the emitter. One such unilateral experiment could be light diffraction. Okay, why? There's something very beautiful about light diffraction. Doppler, if you emit and you move together, what you produce here, you cancel here. So you cannot detect it. But diffraction is different. Let's keep going. Why? Here's diffraction, a laser. Here's the diffraction rating. It has many rays with n can be 0, 1, 2, 3, 4. So you have 1 here, 1 here, 1 here. Okay, and negative also. I just selected, say, n1. So this is the angle of diffraction. The sine of the angle of diffraction is equal to the wavelength divided by the width of the slit. As simple as that. It's a beautiful, simple equation. Okay? So depending on the wavelength, you're going to be here or here or here. Okay. And the position is given by geometry. L tangent of the angle. Okay? So that's the problem that I give to my students, and they get always good answer. It's very simple. 2-step equation. Except that you cannot plug this in here because sine and tangent are not the same. Okay? Anyway, this is the book explanation of the diffraction, which is amazing. This is Huygens principle. Every point of space emits, but I don't care about that. This is the pattern that you're familiar with. Let's keep going now to the Brazilian experience. These people are using the information that Earth is going to leave at the fabulous speed of 368 kilometers per second. Okay? Actually to the left hind leg of Leo. Minus 7.22 declination, 11.2 right ascension. Not my memory, I've done it so many times. So we're going there. Now, they have, suppose that you are not moving. So you have the normal wavelength, okay, here, and you are y sub 0, that's the position where the spot should be. But what happens is that when your instrument is moving in the opposite direction of the light being thrown, okay, throw light this way, you're moving this way, the lambda is going to stretch, okay? Now, if you stretch, you increase lambda, you're going to increase the angle. So this spot, instead of being at y0, is going to be at a bigger distance, y plus, I call it. And they detect this motion of this spot with a fabulous segmented diode, precision of 1 micrometer, or a tenth of 1 micrometer. Okay. I have never been able to replicate it, but this is what they claim. 12 hours later, okay, Leo is here. I know that I should revert the diagram, okay, but it's better to just move Leo like the sun. Now Leo is here. Leo is here at the east. Now it's setting at the west. So now your experiment is throwing light you're throwing light here in the opposite direction, so you're increasing the wavelength. Here you're throwing light in the same direction of motion, so you're going to shrink the wavelength. Therefore, this angle is going to decrease, so here's y minus. So what these guys detect is a change of the position of the spot on the segmented diode from here to here, when either they wait 12 hours or when they rotate the experiment in a turntable. And they get a value which they say is the spread of relativity theory by 21%. I don't understand what they mean by that. You either are 100% against it or 0%. They say 21%. Anyway, what is the explanation of this? That there's a Doppler between at the emitter that is not cancelled by the screen. Why is not cancelled? Because the angle, once you produce an angle here, there's no way that this screen moving in this direction is going to cancel that angle. You can cancel the wavelength stretch, okay, by the opposite Doppler effect, but you cannot fix the whole area in between. You know, this is light, dark, light, dark, light, dark. In other words, the damage is done. Once you open or shrink the angle, the detector cannot help it. You see? So it's like a unilateral effect of Doppler that translates into a change of angle. So this is beautiful. And they have done it in the year 2007. Okay, so this is a prediction. I mean, this is my theoretical justification of their experiment. They did experiment, I have no theory. I have the theory, but could not replicate the experiment. How about that? And those people don't want to talk to us, you know, right? Okay? And they didn't know the reason. We are outcast people. And they're from the establishment. They're in Niterói, Brazil, and they are very respectable 5 Brazilian scientists. Okay, so let's keep going on. Just 3 final words about each of the departments. They didn't know the story of these Brazilian people. Okay, so the discussions, let's go very fast. No Doppler formula, unfortunately, mentioned the time interval between emission. So this is the effect of all formulas. The time difference is omitted. Keep going. The classical formula, however, with its 2 distinct independent velocities, VE, allows us to think of the emission result as separate, distinct, and independent events. Therefore, we discover that even without relative motion, the 2 relative velocities are equal. There's a wavelength shift in the space between E and D, observable from a third frame, which is air. We don't even have to invoke the ether. It's just another observer, third frame. All this allows us to explain the shift of an absorption line, as we have seen, as a result of absorbing edge atom shrinking while the star period stretch. In this way, the correct 656 photons are absorbed in spite of their being stretched to 670 in between emission and absorption. Keep going. I'm just repeating my conclusions. Keep going. Similarly, a light diffraction, this is the positive thing, a light diffraction pattern can be predicted in which the Doppler at the slits and its concomitant angle change is not cancelled by the reception of the screen. This is the candidate to get the absolute or constant motion of the Earth, and I didn't mention the Brazilian side. I don't want to offend them by saying that I justify the term. They would be offended if I do that. Okay? Continue. Now, the relativity view. Can we say that relativity fails to explain the 670 shifted absorption line? That's a strong word, eh? Relativity produces a typical dual affirmation, namely, for an observer on the edge of having an observer, there is no Doppler, because there's no relative velocity. For an observer on Earth, there is a Doppler shift. To explain the absorption, they use the first frame. To explain the shift, they use the second. So you are inconsistent.